The last part of this presentation will focus on results processing. For transient analyses, results come in two different ways. First, one can visualize the distribution of a specific result, like displacements or stresses, over the complete structure for a given time step, like taking a picture. Likewise, when displaying all the pictures one after the other, you can attain the animation of the results through time. The second way of representing the results is the evolution plot of a specific result over time at a given point of the structure, like loads in a bearing. This is an example of animations that can be produced. We can clearly see the motion of the tower due to highly turbulent wind, followed by an emergency stop procedure. The purpose here is to check whether the behavior corresponds roughly to expectations. Designers will mostly look at the plots of specific results that interest them. The type of results available depends on the component, but for most of them, displacements and loads acting on them are available. Specific results for particular parts, like aerodynamic results for blades, are also available. We can see on this small demo that it's very easy to access the results looked for. One just needs to select the one or several analyses of interest and then pick the results in the results tree. It's worth noting that the curve processing tool can be set on full screen mode for easier use. Let's first see the evolution of the rotor rotation speed. Let's also check the torque in the main shaft and the pitching of the blades. Several results can be superimposed for comparison purposes, or to better understand their time-based behavior. In that case, several scales can be used on the y-axis. All of them are coherent here and perfectly representing the classic behavior of a turbine during an emergency stop. The user can recombine displacements along different axes to draw trajectories. Obtaining these trajectories is a simple matter. Just choose the corresponding curves. Here the displacements of the tip of the main shaft on the rotor side. You can resample the curves to be combined to get rid of irrelevant results. And then recombine the new curves to obtain the trajectory. By default, the scale of both axes will be the same, but zooming can always be achieved. Another type of post-processing curves is spectral analysis. This is, once again, a very user-friendly functionality of our curves processing environment. Simply choose the curve for which you want to check the frequency content. Here, we have chosen the torque in the main shaft. Then, click on the Fast Fourier Transform button and go to the FFT Functions tab. It appears immediately. We can clearly see certain frequencies being excited here. If you want to check the exact values, you can print the coordinates of the cursor. A basic FFT transformation gives you the global frequency content of a signal, but it's possible that some frequencies were excited during a short period only, while others that were not showing at the time participated later. This is especially true in the case of an emergency stop. To obtain this information, one can use another powerful tool called waterfall diagrams. These diagrams are basic FFT transformations performed in small time intervals. The color scale should correspond to the y-axis of the FFT transformation, while the y-axis of the waterfall corresponds to the frequency. The scaling and colors of the waterfall diagrams can easily be customized in the dialog box, as shown here. One can clearly see on the results that some higher frequencies were excited by the emergency stop and not by the wind itself. Load distributions can be used as is for local analysis input, but they can also be post-processed to obtain information on durability. In that case, we perform rain flow counts after combining several load cases to try to reproduce the amount of wind that will be experienced by the real turbine. Again, performing these extra manipulations is really easy. Just create a new analysis called fatigue, and define which load cases you want to use. Then for each load case, first choose the time range in which you want to use the results. Then, input the amount of time for which this load case will be relevant in the life of the real turbine and the discretization of the load scale. Then choose which type of elements you want post-processing to be performed on and run the fatigue analysis. One can then plot the rainflow counts that were computed for the different elements. Model analysis post-processing is also quite straightforward. The user can see the list of eigenfrequencies and animate the corresponding modes on the structure. Campbell diagrams can also be plotted to calculate dangerous rotation speeds for each component in order to avoid resonances. We'll conclude by reminding you why SAMSEF for wind turbines loads is the right software to use for those dealing with load computations. First of all, it comes with easily customizable models to run efficient, accurate computations. Load case management is easy thanks to user-friendly definitions and the ability to import them from libraries. Large numbers of runs can be processed quickly when necessary. Post-processing tools are both easy to use and thorough enough for certification purposes and subsequent local designs of structural and mechanical parts. All this leads to substantial savings in time and money during the certification process, as well as on design reliability.